what we are going to look at, I'm sure now you have formed certain groups and you are working on the group discussions, which you should present from next week. So today I'll just take you through some of the work that was done before on RF EMF health issues. So there's a presentation which is online. You can always go through it. It's part of what we are supposed to learn this semester. So this is the website. You guys should be able to reach it, emfhealth.unpowernet.com. So whatever it is that you click on here, there's home, webinar, technologies, which we considered. So long as there's a source of RF, which is not ionizing, then you can discuss that. Then the radiation levels. We have technical papers that were written by students 1, 2, 3, 4, considering different issues. And then the field measurements, which you can go through and see what are the electric field intensities in different areas or in different parts of the country. Okay, so these are just some of the projects that can come out of the studies that you are having this year. So that's just one of the projects. I'm not sure if I'm quite audible. I'm using some Wi-Fi here, which I'm not very sure. Anyway, notwithstanding. So what I'm going to take you through is, let me go back here. Can just go home. So you can take the URL there and somebody wants to be admitted. Somebody raised his hand. This is good. Okay. So we go home. If I'm not audible, you just let me know, but I think it should be fine. So what we want to model first is called, is governed by the ITUT standards. ITU is the International Telecommunications Union. So there are normally recommendations for radio sector and recommendations for telecom sector. So they set, including the World Health Organization, they set the level for the SAR, that is the specific absorption rate that should come from the RF EMF waves, okay, and affect your the amount of heat transfer that can be transferred to in the environment where people are is set at 2 watts per kg. So it means, depending on the source of the RF or how far it is, we need to look within the environment and see what are the kind of radiations that we are having, the radiation intensities, which means electric field intensity or magnetic field intensity. So if you're able to measure one of them, they are normally related to each other. So you can just get the intrinsic impedance and then get either the electric field or the magnetic field. So their effect in terms of heat transfer or power should be 2 watts per kg as a maximum. So we don't want to get into the nitty-gritties of how much does that affect somebody health-wise, because those are a lot of discussions that are ongoing whether it is dangerous or not. So for us, we just take the ITUT standard and say this is 2 watts per kilogram. Then we look at our environment and check whether the intensities that we are measuring are going to go beyond an SAR of 2 watts per kg of tissue. Okay. But the measurement equipment that we have would probably just give you the power density and electric field intensity at certain frequencies. So but you see, you cannot be very specific. In the environment, there's a range of frequencies. So it depends on the equipment that you're using. I think we had used one from 30 megahertz to 3 gig. which actually that's within the space where there are a lot of TV, radio, and GSM communication systems fall within that band. So if you have such handheld devices, you should be able to get the integrated total about electric field intensity in the environment and then convert it to the power density and get the SAR. Now, SAR now, that means then you're dividing by the mass of the tissue that you are considering. So it could be the tissue, could be the skin, which is outward. If it is not the skin, then after the skin, you may have some fats or the meat layer, and then you go to the bone and then the brain. So you can consider that. And now you see you'll be having power traveling through different tissue, and they have different electrical properties like the permittivity, permeability. And what you consider, most power travel through the skin depth only. Okay, so you have to see how much is it, about 63% within the skin depth. So that will go through the skin depth. So it means the next layer would only have a 37% of that power. So you can do that calculation among layers until you reach the brain. So it means then in our case, we would have to calculate the skin depth of each layer, right? So the model of the SAR, so we'll define what that SAR is. We have said is the specific absorption rate. But the depth to which radio waves penetrate the exposed tissue depend on the frequency of the source and also the electrical properties. And we know the skin depth is normally given by that expression. Delta is equal to 1 over pi f mu times the conductivity of that tissue, right? So if you go to that page, you should be able to make your good notes. So the factors that you would want to consider when you are carrying out such experiment is the density of RF antennas. If you are in urban center, you expect that there will be so many antennas. Even if you go to the CBD, you'd find several antennas on the street and on top of buildings. So it means then the RF environment within urban centers compared to rural or metropolitan areas or educational centers would definitely vary. Okay, some people cannot be admitted. Okay. So it will definitely vary. Then also the frequencies, because we have seen that the skin depth depends on the frequency. The higher the frequency, it will be a smaller skin depth on the surface. This means you'll be affected more because that heat will be concentrated within a very small layer. So the frequency of use would depend on the technology that we are referring to. So for example, if you're talking about 2G, a certain frequency, the center frequency that are used for 2G, 3G, 4G, 5G going forward. Wi-Fi, which is on either 2.4 gig or 5 gig. Internet of Things, okay? And also, there are always different, if you talk about 3G group, discussion group, 3GPP, a power class, it means that you could be on a 4G, but in your environment, you're using power class 1 or power class 2 or power class 3 or power class 4 for transmission. So again, we have to consider what power class are you utilizing when you are, because what is important here is the RF that you have in the environment would also depend on the EIRP, the power from the transmitted power. So we'll see how it is related to that. So these are key factors to consider when you are modeling the RF environment. So how do we define SAR? So specific absorption rate is the rate at which that energy is changing per tissue mass. So you have d over dt of dw over dm, where that's the energy will be w and the mass is given as m. So then we have d over d of w, d dw over dm dt. So you can see dw over dt is actually power over dm. Okay, so it means we just need to compute power here. And so if you have power, it's v squared over r, right? V squared over r is power, and that, you know, is related to the electric field intensity. So you can have the mass. So you have, you can relate the power to the electric field intensity using the equation for, if you think about the potential difference, okay? So it means then that V can be related to E, where you have V is equal to E times D. So that would mean that you have D squared in the bottom part. Then now you have the mass. So that would give you an area in the bottom part, and then now will be a volume. So it means then mass over that R cubed there would give you the density. So you can express the SAR in terms of conductivity times the electric field intensity over 2 times the rho. But that 2 is there because you cannot calculate 2 from V squared over R. So here, 2 there just means the RMS value. Okay, so we are actually taking the effective value of the power. So it's the RMS value that we're computing. That's why dividing by 2. So that's how you express SAR. So this is the measurement that you can have physically. So E is easy to measure from using equipment. So it means if you have the tissue that you're considering, and you can get the conductivity of that tissue and the density, the tissue density, then all you need to measure from equation 1.1 is the electric field intensity. So if you get the electric field intensity and you know the tissue density and the conductivity of that tissue, then you can compute the SAR. Okay, so W is the absorbed energy, M is the tissue mass, tissue density is rho, potential difference V, resistance, and then conductivity and surface area, electric field intensity. Now, the tissue power density is of course the radiated power, which depends on what you are transmitting times the gain of that antenna. So you have PT times GT over the surface area. Remember, this is now you're considering as if the antenna was isotropic. So is that volume of the sphere, so the area of the sphere around that antenna. So assume my isotropic antenna. So the power density is P, the transmitted power times the gain of that antenna over the area, 4 pi d square. And that can be related because this is now the power density is equal to the electric field intensity squared over eta, just as what we did in equation 1.1. So you get E squared over eta. Now eta is the intrinsic impedance of that tissue again. So it's given by, so that's where the electrical properties come by. So eta is root of mu r over epsilon r times eta naught. Eta naught we know is 120 pi. Yeah, it's 120 pi, which is 377. So depending on the tissue, you can actually calculate if you know the tissue properties, you can calculate the eta there. So you have PT, the transmitted power, and gain at the transmitter. Now D here is the distance, D, when you're considering the power density here, D is the distance from the antenna to the tissue. But now it includes the depth of penetration. What that means is the distance in which you are calculating the surface area is from the antenna. So it's the D in air, the distance in air, and then let's say you are considering the skin, your skin. So at the point at which you are considering that would mean we are considering this at the skin depth. So it will be the distance in air plus the depth in your tissue. So that would be dA plus delta, where delta is the skin depth. So D is equal to dA plus delta, with dA as the distance in the air. Okay, so all the tissue properties that you need is the permeability, relative permeability, the permittivity, conductivity, and Now you calculate the tissue density, meaning you know the mass, so over the volume. So these values are constants. They are values that are known from databases. So if you can get mu r, epsilon r, conductivity, that is sigma and rho, then you can compute the SAR at any given frequency of your choice. All right, so if you're able to derive this and show the equation for the tissue density, somebody tried to do something, I don't know. All right, so if you get the equation for the SAR, then you should be able to manipulate the any work to do with the SAR, whatever it is that is asked about SAR, depending on the tissue. So if I asked you about to calculate the SAR in the meat layer after the skin layer, what would happen is that at the skin depth of the skin tissue, you'd have like 63% of power just confined within that skin depth. So it means then the power that would be transmitted towards the meat layer, let's say you don't have a fat layer. So the power that is transmitted towards the meat layer would be just 37% of whatever was at the surface of the skin, right? Because the rest is going through the skin depth of the skin layer. So 37% would proceed towards the meat layer. And then you check the skin depth within the meat layer, 63% would be within the skin depth, confined within the skin depth, horizontally on the meat layer. So what proceeds to the bone layer would be 37% of that value. So that's how you get it. And if you want to look at some of these papers that were done by students before, we can see what they did in paper 1. I hope it's going to open here. Seemingly the Wi-Fi is not very strong. So here they were investigating the SAR values for LTE, that is 4G, under different modulation schemes. So they have 64 QAM, 16, and 4 QAM. Now these modulation schemes, it depends. You need to check the power, transmitted power, the gain of the antennas that are used, and also the power class. So if you read this paper, you should be able to see more on how the students were, whatever they used to analyze the SAR. So that's what it is. So they were analyzing here power for LTE. You can see how you determine the power of a user equipment for LTE. Then the modulation types for 4G. Okay, 64 QAM or what they were trying to analyze that power there. The skin depth there, power skin depth. Of course, power skin depth is the depth within 63% of the power that is dissipated. So that would be half of this normal skin depth. The skin depth in equation 7, if you're considering power skin depth, it will be that divided by 2 because of the power attenuation of equation 9. You can see that. So the transmitted power, they're able to calculate that based on those equations. The SAR can be changed to equation 11. Don't worry about that for now. Okay. So there they did for 16 QAM. Power, you can see on equation 16, for the user equipment, the power that is used for transmission is 4 milliwatts. Okay. For 16 QAM, 0.25 milliwatts, and for QPSK, 0.01 milliwatts. Okay, so you can see. So it means if you are now, then you get the tissue properties in a table like this one. So you can see the relative permittivity for the skin. This is well known, so you can get this from databases. Let's look at a few of the parameters. So tissue properties are actually at different frequencies. So at 1.8 gigahertz, you can see they're quoting reference 10. We'll see what reference 10 is. So the skin relative permittivity is 38.9. Conductivity is 1.25. Density of a skin is 1010. Thickness 0.001. 0.01. And the power delta, the power depth, that's just half of that, which is 0.0053. Then the fat, relative permittivity of the fat is 11. You can see the permittivity for the bone is high, the brain is even higher, 46. For the fat is very low, 11. Conductivity, the skin and the brain very high, okay? As also tissue density for the skin and the bone, of course. The bone is higher than the brain, but you can see the brain is the second to the bone. So using those properties, you should be able to calculate the SAR in theory. So they were able to do the SAR profile. You can see figure 2. You can actually go to that website and see paper 1 if it's not very clear on my side. So you can see the SAR values. What I can see here for the 64 quam. So there's a value there for the skin. Because of those tissue properties, you can see the skin is high, the value is high. But when it goes to the fat layer, it drops. It climbs a bit for the bone layer, all right? And then now climbs for the brain because of high permittivity in the brain, okay? But at the center of the brain, you also consider now why this at the center of the brain, why is it coming low? Because this is really far from the surface of the skin, because of the skin, not the skin depth, but how far power is coming. And here also we are considering, they have to tell us when they are calculating the SAR, how far is the antenna? How far is the antenna? So if they are calculating it from a 4G phone, then they need to tell us or you need to tell us how far is that. You can see D here is 10. How far is the user equipment from your skin? Okay, so they must have specified it somewhere. Okay, the constant value chosen, which corresponds to that, given a value of that, then, and D is equal to 10 meters. Yeah, so this, probably the antenna is 10 meters away, because that will affect, because if you look at the SAR calculation in question 11 here, you see the distance here, D phone. Centimeter airspace D phone is applied only in the first layer. Okay, yeah, that's correct. So how far is the phone from your skin? So that is very important. So it will help you calculate the SAR correctly. So if you move it away from your skin, definitely you have a lower value of SAR. If you move it very close, a higher value. You can even put zero distance, like you put the way you put your phone on your ear. So it means there's zero distance. So D phone will be 0. So you only have the skin depth. So again, you calculate the SAR, you realize it's the highest. Okay. All right. So that's one way of investigating the SAR values. There are many other ways. I'm sure you can read the other papers. They're simple to understand. So just go through them and see what your fellows did. Very good job that they did. Then we can have a look at an example. We try to put a calculator there so that anyone, not necessarily an engineer, may also just want to check using the home equipment or home devices that you have. You just want to see how dangerous could they be based on ITUR standards or World Health Organization standards. So in that case, you can come here, you can go to the SAR calculation simplified and determine just, because now we have seen that it depends on the distance of this tissue from the radiation source, RF-EMF radiation source. So then that means then we need to study how then does it affect an adult, because we know the size of the head of an adult compared to an infant will be different. And then we also check, on average, does it affect ladies more or men more? So those are some of the ways in which you do research. So you can come to the simplified calculator, and then here you can choose whichever technology that you want to test. So you could have a microwave oven at home, Bluetooth device on your laptop, a Wi-Fi access point, a 5G antenna, 4G, 3G, 2G, or GSM 1800. That is the BTS, or GSM 800, 900, also a BTS, a different standard. So you could have both 800, 900, and 800, 1800, 1900 on the same sector of a BTS if you're doing co-location of antennas. So for example, let's choose, maybe somebody just at home and they just want to check. He has a 3G phone or a 4G phone, He's not an engineer, but able to understand this calculator. So you just choose, you want to check a microwave oven. So that's the technology, it's a microwave. So that's the frequency that determines that. Then you go next. So what is the RF source? Because we have chosen microwave, we cannot use my oven. If you choose a phone, it should not be able to go. Let's say the effect on a male, you see, it will give you that exception. So that's not compatible to microwave technology. So you make a new selection for RF device. Okay. If it's not in the list, you select others. So we go back. So technology is microwave. So it means here we have to choose either others or microwave oven. You want to test it. Most of the concerns we got before we started this project was somebody complaining, wanted to know whether she needs to put a Wi-Fi access point in a bedroom, as people do, or in the sitting room. How much does it affect a child? So then we said, okay, let's see whether there will be a difference between an infant and an adult. And then later she said, my child is a girl, not female. It's a female, not a male. So again, we had to check between male and female. What will be the difference? So these are the concerns of the users or the public. So you have to look at that. So my source is oven, and the RF source, the edge set, let's say infant, and the infant, let's say female. Then we go next. How old is the child? So age for infant will give you 0 to 36 months. I think I'm being called to go for the conference already. Hello, Doc. You're coming to my hostel? Yeah, sure. Okay, fine. Cool. All right, guys. So there's a conference that we are in. So what I'm going to do, so let's say I'm being picked in a minute. So here is 10 months. Let's go next. I'll just give you one example, then you can proceed with other examples in my absence. So you have 10 months, then we go head size. Now head size you can't change. So that's the average head size of an infant who is 10 months old and is female. Okay, is 6.8. Let's see male. What would male be? Next. Then you see male is a bigger head. So males have an average bigger head. So let's go back to the one we're checking. So I just wanted you to see that. And then next, same 10 months, so goes back to 6.8. So those ones you can't change. Those are from CDC. Then RF source, how far is the microwave? You're carrying your baby and you're near the microwave oven. How far could you be? 10 centimeters. And you want to see the effect on the skin. So you calculate. You can see the SAR result is 1.36, very close to the limit, which is 2 watts per kg. Let's change that. What if you move closer? 5 centimeters. You get 13. Very dangerous. Yeah, but you see also how quickly it degenerates. 7 centimeters away from the oven, 4.6. 8, 2.9. What about 9? So those are dangerous levels. 1.9 also almost dangerous because that's just near the limit. So you can see that. Then you can now check your details there. All right, guys. I have to leave. We will just be online. So I'll try to be in class again tomorrow. We just try. I think tomorrow I should be there. The conference is ending today. So just try some of these, different technologies and see what you are able to get. Any question before I disappear? Okay, so it's only for today. For the rest of the classes, I will be able to attend. Okay, register your attendance, then you can leave.